Okay, welcome back, guys. So we're talking about the importance of the mathematical abstractions about our device. So why we need to have understanding, of how these parameters, the electrical parameters, can affect on the higher level the performance of our digital logic. So talking about the threshold, the switching voltage. So the switching voltage also determines that's switching point also determines what the digital the logic gates would see as a 1 or a 0, that is a high or a low. So let's say, for instance, let's say kn is far greater than, if kn is far greater than kp, what can you say about this whole expression here? So if kp is far, let's say, okay, let's use far greater than, let's say kn is far greater than kp. What happens? This whole sodic this parameter here would go to 0. If kn is far greater than kp, it go to 0. So all the terms will go to 0 and the denominator becomes 1. Then you have threshold only. So that means the switching point voltage would be around the threshold voltage of the CMOS or of the MOSFET, right? So that's one scenario. Another scenario, it's if kn were to be far less than the kp. So if it's were to be far less than the kp, that means this whole sodic parameter here would be so large that we can ignore the threshold, right? Then it's also for the denominator, it will be so large that we can ignore this 1 here. Then at the end of the day, you have the sodic expression parameter multiplied by this VDD plus VTP, then over the sodic parameter, so that then you would have the sodic parameter cancel out, right? So at the end of the day, you would have the VM to be approximately VDD plus VTP. So that is, VDD would the threshold voltage, the switching voltage will be so close to the VDD. Yeah, we may not want that, because it means there is no enough room for the high abstraction. So you don't have so much for the representation of the value 1, that's I. You get I maybe we can talk about this more for the mathematical, but I just want to give you guys insights. So that means the best usually may be to make the kp and the kn equal. So let's see what happens if they are equal. So if they are equal, so basically you have the sodic expression, it goes away because they cancel one another, so you just have 1. The same thing, 1 here, so you have 2 for the denominator. So at the end of the day, you have approximately VM to be VTN plus VDD plus VTP over 2. Many times VDD and that the VTN, that's the threshold for the NMOS, and the threshold for the PMOS, they are most times usually close. So, and they are usually the negative of one another. So that's in the numerator, you may have the threshold for the NMOS and the PMOS cancel out. So for the numerator, you just have VN left. I'm sorry, I can't. I think it would have been better to be actually writing this out. Let me see. I don't think I can do this on this. It's not possible for me to write, but I hope I'm just drawing inside so you guys can just see. So at the end of the day, you just have approximately VDD over 2. That's better. That seems better, because for your low, you would have enough room, because so everything that will be low would be anything from 0 up to half of the VDD. Then anything that will be high would be about that half of the VDD to VDD. Unlike the previous ones, for the first one, when it was I think when it was far greater or so, or far less than, you have you just had VDD plus VTP. So that is, you can, all that is low would be 0 to the VDD plus VTP. Then maybe all that would be high would be from that VDD plus VTP to VDD. That means you don't have enough room for what is called high volt, and that's a high logic. Then the same thing applies for it will affect the low logic. So noise margin will be very bad. So at best, maybe we want to do we want them to be equal. So we want KP and KN to be equal. So take note now. So if KP and KN are equal, so that's these two terms. Look at equation 5.18 and equation 5.19. I really wish I could write. Maybe for next time I would get something to write, but for now, just the insight. So if KP and KN, we make them equal, because that looks like the best thing to do, right? So we'll try to make them equal. What do we get? So let's leave the sizing. Sizing is at our own control. Let's just leave that out. So you notice that, remember that generally the mobility for electron is greater than the mobility for holes, and it's about 2 to 3 times larger. That's the mobility for electron, right? So that means at the end of the day, you would have one side of the equation greater than the other. So you have something like W over L, let's say, so you have twice the mobility of P equals to W over L of P, the mobility, the transconductance, the mobility, and the Cox for P. That's that. Then to balance things up, already the part of the equation for the Kn, for the NMOS, it's already looking heavier than the other side. So I think usually what will now be done, let me check time. Okay, I just used 7 minutes. Okay, so guys, so saying the mobility for electron would be greater than this. So let's say this transconductance parameter, let's just say we represent it with beta. So that means this part of for NMOS would be W over L of N will be equal to 2 to 3 times beta. Then for P, it will be W over L 2 to 3 times. So let's just say 3. Let's pick 3 for instance, or let's pick 2. So that means you have W over L of N twice 2 times beta, right? Then you have W over L just beta alone. So beta means the transconductance parameter, that's this, stands for this mu Cox and all. So one thing we know from device physics is that the beta of this will be twice or thrice, but let's just pick 2, so twice the beta of this. So at the end of the day, so when you try to equate, you remember we said making them equal will be the best for noise margin, right? So when you equate both of them together, the beta on the left hand side will cancel the beta on the right hand side. So at the end of the day, you would have W over L of P is equal to twice W over L of N. So what's the implication, or what's the there's something here we have to, this is telling us, it's telling us that if you want for the best noise margin, that's where the switching voltage is half of the whole available voltage, that is half of VDD, about half of VDD for if you want, if because that looks like the best case for us, if that's what we want, you need to make this kn and kp equal. When we did further breakdown, we now notice that at the end of the day, it means that the sizing for PMOS must be twice the sizing of NMOS, which makes sense physically. What's the physical implication? When you have this, you have the PMOS, the NMOS. So by mobility, electron having more mobility than O's, it means NMOS will be quite faster than PMOS. So you're putting two things with different speed in parallel. So what do you need to do? You normally, this PMOS is not as fast as NMOS, right? So but they can't, and you want them to operate together, so you need to compensate for the slowness, the inherent slowness of this guy, the PMOS. So by doing what, one way we can make, though it's not faster, but we can make it, work up to the capacity of the NMOS, is to make it wider. By making it wider, you make more electrons or more carriers to flow through it. Yeah, that means you have more carriers flowing through it. So that way it will give the notion of, oh, okay, the NMOS is the PMOS is as fast as the NMOS. So by making the width, not the length. If you're making the length longer, you'll be making the PMOS slower. You get? So what you need to do is to make the width of the PMOS wider, so that way it will be able to operate at the same capacity with this. Or better still, you can make the length of the gate of the NMOS longer, so that way you want the NMOS to be slower, so that it can match the slowness of the PMOS. So either would work, but what we'll be working with, it's varying the length, the width, not the length, because many times the length specifies the process node. So if it said if it's 180 nanometer, so most likely you want the length to maybe be the same thing for all the transistors, all the devices there, you get, for one reason or the other. So at best, so you want to just vary the width. So that's what we're going to be doing. They would have the same length, we'll give them the same length, but we'll give them different widths. And for the best that we've learned from the device physics, from the theory, the best to do is to make the width of the NMOS, the width of the PMOS wider than, so at least twice the width of NMOS. So let's say for the NMOS, so let's now specify. So time to size them. So you want to size the NMOS, so all you just need to do is double click while you have your cursor over the NMOS. You double click on it, then you have this come out. So the name, L for the length, W for the width, NF is the number of fingers. This would get I would explain what this means when we get to layout. This is a layout, it's more a layout term than a simulation thing here, but yeah, you can actually leverage on this in your simulation phase so that you can make things better. So many times, the whole goal is to shrink, to have your whole IC to be smaller. So you may, instead of having a big device, you can just divide them as if there are several devices making up one large device. So then M for multiplicity, it's like more of the synonym of this number of fingers, NF, but slightly they vary, but they do the same work. But so for now, we're just going to focusing on W and L. So for, let's say I want the length, I want the node, let's say I just want it to be let's say 300 nanometer, so that's just 0.3 microns. Yeah, so That's for the length. Then the length will be the same for the NMOS and the PMOS, but now the width, let's say I want it to be I want it to be, let's say, 1 micrometer. So 1 micrometer for the width. So I'm done. I just press OK. Then I'll come to the PMOS. Like I said, we want them to have the same length. We're not varying the length. We're trying to be strict with the length, as in the process node. Let's just assume we're just want the length to be fixed. Then that's 0.3 micron or 300 nanometer. Then the width, so like we've said, the implication of those theories we've seen is that you make the width of the PMOS twice the width, or at least twice. You can make it thrice too. So it was 1 there, so I can make it 2 micrometers. So okay, so yeah, we're done with the sizing here. So let's quickly now come back to the whole simulation thing. So we talked about SPICE directive. So this is the interface you give your SPICE directive. To save time, I'm just going to come here. I have a directive here already. I'm just going to come here and I want to copy the contents. I want to copy the content here. It's not just to save time. Okay, so for yours, please take note. So this what you this netlist will be available, or the schematic this thing will be available, so you can use. Perhaps you can just copy directly to, but you can, in case it's not available, or not to delay you can just follow this. So name equal to ngSpice. So I'm just using ngSpice because I want to simulate with ngSpice. ngSpice is a simulator. Well, many of those simulators, there's HSpice, there is PSpice. So this is ngSpice. Then just follow this through. Then you start with the quotation mark. So now, everything inside this quotation mark would be where your SPICE directive would be in. So dot trans means I want to carry a tran, means I want to do a transient analysis. Dot DC means a DC analysis. Sometimes you may have so many directives, so you can just put all the dot directive into just one single directive called dot control. So once you have this, all the dots, so for instance you want to run a transient analysis, you don't need to put a dot again, you just say tran, then that's all. The same thing, normally you should have, maybe I think plot, is it dots or so, but I'll just put it that way. So anyone you want to use, anyone. So our first analysis, I think, we should do the transient. So like I told you, it's more or less like a code you're writing. So if this asterisk here means I commented this guy out, so when it's running, the simulation is running, it won't see this transient analysis. So to uncomment, I'll just remove the asterisk, so it's uncommented. I just want to carry out transient analysis alone, so I comment the .dc analysis, and so that's so dot control. I just wanted to save the all this I would explain later, step by step. Let's just have this first. Okay, so you can see I can see the code here, and So if I want to carry out transient analysis, most likely you want to give the input voltage source would have to be a time varying kind of source. So for digital simulation like this, I want to use a square wave, right? Something like that, something that looks like a square wave. It rises, then it gets flat, maybe that will be a 0, then it comes down again to be a 1. You get, so to do that, that's my V, that will be my V in, that I'll make a pulse kind of square wave or a square wave voltage form. So I'll just double click and I'll just remove that 3. So I'll say value equal to, then pulse. So that's pulse means the kind of voltage source I'm specifying is a pulse voltage type that will look like a square wave. If it were to be sinusoidal, I'll just do sine, then I'll just give the parameters. But for pulse, that's for the square wave, I'll just do pulse. Then like I said, it's all like a code, like a command. So there is this book I would share with you guys. It's the manual guide for ngSpice. Like I told you, ngSpice is a spice simulator. All spice simulator understand the same language, which is called the spice language, if you want. Yeah, so if you know ngSpice, you know other spice too, hspice, pspice, and name them. Yeah, so it's a user manual. You can, all the old syntax you need, you have them here. I'll share it. So so if I want to specify a voltage source, the syntax are not okay. For sinusoidal, this is the syntax. You just do sin v naught, that's the offset, va the amplitude, but it's not a voltage a sinusoid we want to specify, so it's a pulse, right? So I don't know if I've passed that of pulse. So this for pulse. So these are the parameters v1, v2, td, tr. So this is what they all mean. v1 means initial value, v2 means pulse value, td means delay time, tr rise time, fall, and also those are things you need to specify for your square wave. So for mine, initial value I can just make it 0. I just want a simple square wave. So 0, that's the initial value. Then v2 is a pulse value, 3.3, because I'm using, for yours it's going to be 1.8 for the Skywater. Delay time, I don't want there to be any delay, so that will be 0 nanoseconds. I need to specify the unit. Then the tr for the rise time, it should not take much time to rise, though a square wave, perfect square wave rises instantaneously, but it's not ideal. So let's make it less ideal. So let's say just use, let's say 2 nanoseconds or just 1 nanoseconds to rise. Then the fall time, the same time, it should be uniform. Let it fall just using 1 nanoseconds. Then the pulse width, that's how wide should be the square wave. Let's say it should be as wide for, let's say it should last for, let's say 20 nanoseconds, or let me make it 50 nanoseconds. Should last for 50 nanoseconds. The period, so how long will it take to complete a cycle, so the up and down. So I want to give, for the downtime, I want to make it equal, so it takes 1 to rise, 1 to fall, then 50 to remain constant, so that's like 52. So for the next, let's say for the next 52 nanoseconds also, let it be reading 0 before then the subsequent 52 nanoseconds. So that at the end of the day, that means the period, let's say 52 times 2. So is that looking like 104? So then NP is the number of cycle. You can just leave it like that. If you don't specify it, it would be the default. It's infinite. It will generate more square wave for you. So I think one more thing that needs to be done is to, I think the spice does, whenever it encounters white space, I think it stops there. So to avoid white space, I think using a comma would be good. So everything you need would be from, so for instance, for the DC analysis, you want to know for the transient analysis, if you want to know the syntax you get, so you can just come and search .tran. So .tran, let me see the first suggestion here. What is it giving me? Okay, still not giving. I need the one with the syntax. So I think that one is around chapter, is it 15? So chapter 15 exactly. So this is it here. So .transient, and so this is the syntax. .tran, the time step, the step time, the stop time, and the start time. So the first parameter is the step time. So how much, so if it starts from so and so value, and how much, so, and it's going to stop at this value, by how much should it jump to this value in steps. So step, stop, and start. So let's go back again. So for mine, you can just say I only specify 3 values, so only the step and the stop. The starts was not specified. If you don't specify the starts value, the default value would have to run for it. So the default is 0, so it will start at time 0. So I left it that way. So for all your simulations, you can just use the ngSpice and other syntax, so you'll find them there. I'll share that also. So let me just adjust this guy, or let me adjust this first, then move. Okay, so yeah, I think we're good to go, but let's still see what we have here in our spice directive. So now, having known, you know what this means now. What it means, you want to do a transient analysis. This is step time and this is stop time. One parameter is missing, but the default value will be used, that it will start at 0. Then so some control statements here. So since I want to run transients, I told it to save the important nodes I need. These nodes are important because I want to plot them. You get, when you're running a transient, so you want to see your plot, your transient, your DC, your AC, you want to see the plot, right? So I'm trying to tell you to save the plot, to save these variables in advance. That's what I'm going to plot, because I'll later tell it to plot those values, so it will keep them for me, so it will keep them for me. Then when it encounters the directive that says plot, it's something that it has saved already, so it will be able to plot them easily. Then I give it the instruction that run. Then this tran is here. I've commented it out. I have already given this the tran directive already up here. So, but just in case you, like I said, all the dots directive, you can put them inside the control. So just in case you want to put the tran inside the control, it has to come after this, I think so. It has to come after the run. You need to tell it to run first, then I think so. Yeah, or the other way around too can work too. Then the next thing, but before you tell it to plot, you must tell it to run. That's the main thing. So plot. So what do you want to plot? I want to plot v out and v in, and you must specify the node correctly. For instance, all these node names are case sensitive. If you're going to go and be using, if for instance I used capital letter for the v in, right? So and I told it to save small letter v in, there will be problems, so I better put the right thing. Then my v out, it starts with capital letter, so it's small letter, so it's all fine. Save v out. Then plot what? I want you to plot v in and v out. What type of nodes are those? Like what do I want to, what about those nodes I want to plot? I want to plot their voltages, the voltages at that node, right? So this v before the parentheses, it means voltage type. That's the kind of plot I want to do. So it should plot the voltage at that node, so the voltage at this node v in. So then when you start a control statement, when you're done, you need to end the control statement, so by using dot end control, that's c, end c. Then you have this quotation mark at the end because you started with a quotation mark, the value, so quotation mark, then so yeah, then okay, and you save. Yeah, so save the file, yes. Then I think we're ready for simulation. So when you're done like this, the next thing you need to do, and when you're ready for simulation, you click the netlist button here. So when you do that, if there's any error with the netlist, the netlist will flag. When you click the netlist, it will flag that there is error somewhere. So let's do that to know if there's error too. Okay, nothing is coming up. That's because I have not set the option. You can actually set the option that would say, okay, when you click the netlist button, that a pop-up window should come out. So you go to option and show netlist window. So show netlist window. So now when I click the netlist window, so when I click netlist, it generates the netlist. So you can see this is the netlist. This is like the code actually. So this, I would have written this thing myself, but you can write it yourself. You write a netlist, or you just use the schematic capture. Then at the end of the day, everything would be interpreted as this code, so that the simulator will readily use. This is more in use for the simulator than these schematic captures. These are just graphical representation. This is the main thing. So you can see, all what's this XM1, that's a M1 transistor. I think that should be the PMOS or so, or no, it was the NMOS, since NMOS was the first transistor I dropped first. Then the second is the PMOS. You can see the definition. All this, maybe later we can come back and talk about how the netlist works, like all these connections here. Then the voltage source I specified, this is the V1, it's just 3.3 volts. Then this other one, it's a pulse type of voltage to generate square wave for us. And look at the capacitor, and look at our spice directive here. So, and it's giving us, when we click the netlist, it gives us the netlist full, like we can see everything. The advantage of this is when you get to understand spice language, you'll now be able to go through it yourself and confirm that everything works well. Yeah, but sometimes the simulator does it in a way that if there's any error with the graphical schematics you've made, it won't even show anything. So it will tell you that there's error, then that way you know that there's error. So that's the advantage of generating. So after doing that, you click the netlist, you get the netlist window, you go through it maybe by yourself, or if there's any error, it will just tell you that there's error somewhere. Then you can just cancel the window, or you can do dismiss, you can do save, anyone you can do. So that's all. Then you're done. You click this, we've done that. Then next thing, you click on simulate. Then yes, good. So now there was no issue with our netlist, Spice netlist, as far as the whole language Spice language thing is concerned. There was no error, but now this is telling us, Spice is telling us there is error. So what is the issue? What is the error? What is the issue? It's telling us that it can't recognize the sub-circuit. So sub CKT stands for sub-circuit, so unknown sub-circuit. So what's the sub-circuit? XM1, that is the transistor M1, and even perhaps the transistor M2. So what's the problem? It can't, this is an object, remember, all these are objects, so it can't recognize it, and it's only that object, this transistor object, it can't recognize. That's because this is a scheme. A scheme is different from ngSpice, and ngSpice is different from the PDK you're using. So these are different party objects working together. So a scheme just help you get this together, So from a scheme, you picked this component that belongs to the PDK you want to fabricate with. But when you try to simulate, there is nothing telling ngSpice where this belongs to. So to ngSpice, this is an unknown object, so you need to tell ngSpice where this belongs to and where it's located. So ngSpice will get all the parameters. So you can see it's telling you unknown subcircuit, so it can't relate with all the W over L, all this the side area, the source area, and the source perimeter, all of those parameters defining the transistor. It can't relate with it, so we need to make it known to the ngSpice. So how do we do that? So actually I missed something out. So this is how you do that. I have it. So you just need to specify the directive, the directory where the PDK object are located. So you need to specify it also in this interface. So that's what ngSpice will now use to go and trace these guys, and then would understand the parameters of these guys. So what I usually do is, so this is what we need. This contains the directory. So all I just need to do, I need it, right? So I just need a copy of it. So select C for copy, but not DJ copy. So I bring it here and I have it. So for your Skywater, it's going to be different. So this directory, this part, it's already for Skywater. When you load the Skywater, you have an interface like this. That's this very thing here, like this for Skywater. The good thing for Skywater is that you have it here, so you can just, but I don't have it for the Global Foundry Zone, so I had to just find a way around it to get it. So the good thing for Skywater is that if you have it, when you have it there, you can just do the same thing and copy it, you get. So that's you still covered for that. So after doing that, you Control S again, you save, you again repeat the process, excuse me, netlist. Okay, as far as the netlist is concerned, nothing is wrong. Okay, so anyone you want to do, you cancel, you dismiss, you save, it's all fine, it doesn't change anything. Then simulate. So okay, it's simulating, no problem, and it's simulated well. It did the transient, it went through this control statement, it's plotted, you can see the plots, and you can see the summary of the whole simulation it carried out. It gave you the temperature at which it carried out the simulation, 27, about room temperature, it's the V out, the 3.3, the V in, all this is later. For now we don't need this, so we'll get to see what all these things really mean later. Oh no, everything went away, sorry, let me simulate again. So this is what we're interested in. Now let's see if our CMOS inverter is inverting. let's see. So the blue plot is for V in and the red is for the V out. So for this time space, this time period here, the V in is high, so that's it's 3.3, so it should be reading 1. Then we should be expecting the output should be reading low. But what is this? This is just it's not dropping. Okay, it tried to drop, but it's very, very slow, very slow. So before even the next phase, it has not even finished dropping. The highest it could get, it's the lowest it can get to is 1. Then before the input changed to 0. Then when input changes to 0, you're expecting it to now rise to be 1, right? So look at it, it's still struggling again to rise. So I can tell you what is causing it, and maybe I'm glad I had to do it. So this is actually what is causing it, is this capacitor. So you can see that the capacitor is affecting the performance of our inverter. So you can see that's the importance of trying to model the whole environment. We're trying to model the environment where this guy will be working in. So it means if you make this your CMOS inverter and you try to load it with another gate, maybe another inverter, and if the capacitance of that gate is the input capacity of that gate is about 10 picofarad, you will not be getting a good result. It will load it will have a bad effect. Let me just do a proof that okay, it's the capacitor that is affecting it. I'll just disconnect this capacitor from here briefly. So let me just move it away. No, it does not want to move. I'll just delete the wiring there. And in order not to have issues with the netlist, let's see if it's going to have issue, because it's left unconnected, so it may see it as an issue. Okay, it seems like it's not having issue with it. Let's just go ahead and simulate. So now we can see with this our inverter is inverting. So how do I know? So we have, at this point, this is the input, blue for the input, red for the output. At this point, when the input is high, 3.3, you can see it's red here. The red is low, it's at 0. Then when the input dropped, the moment the input dropped to 0, then it inverted, the output became 1. So you can see with this, our inverter is indeed inverting. So so what does this mean? It means this, if this is the load you want to use, that you want the inverter to drive, the load would affect the inverter's performance big time. So maybe what we can do is perhaps we can so maybe what this capacitor is doing is shorting, because with changing voltages with frequency, capacitor becomes a wire. So maybe the capacitor is shorting for the it's a pulse voltage, so it's changing. So maybe the rate at which the pulse is changing is enough to make the capacitor a wire, so it's just shorting the output to ground. So we want to reduce that effect. So what can we do with the from the capacitance perspective? So that is, we if you don't want the capacitor to be more a wire too much, just a wire, so I think what we want to do is to reduce the capacitance. So let's see. Let's see if there will be any change with 1 pico. Okay, so you save netlist. So it looks better though you can still see the output is struggling. Like it's not as perfect as the output, the input. You see the input, it drops immediately. So when the input becomes 0, yes, good thing is that yes, the capacitor, the output now rises. It rises to become high, but it's taking time. There is a ramping effect here somewhere. It's taking time. So the lower the capacitance, the better you get. Capacitor causes delay, so that's when you talk about propagation delay. The more the capacitance, the more the RC, the more the delay. So let's do one more experiment. So let's just reduce it further. What is lesser than pico? So let's just make it femto. So small letter f. So let's see. Wait, let me cancel this. Okay, so netlist. Okay, no error. You can see. So femto looks like the ideal case. So now you can see how capacitance, output capacitance can cause propagation delay, and how it can affect the performance of the CMOS inverter gates. So I think that will be all for transient analysis. Yeah, and I'll just stop the video here, then we can go ahead and do a DC sweep. That's the DC analysis. Yeah, thank you.